Now that we've talked about VPN connections, we can move into the second category of WAN links, and that is leased lines. Now, leased lines was something that we talked about in the icnd1 series. It was actually the only WAN link that we talked about in icnd1 because icnd1 was geared around the small business world where WAN links are a rare occasion. Most small businesses have a single site and just a basic internet connection. So what I'd like to do as we get into icnd2 is do a little bit of review. I know it may have been a while since you saw the leased lines in icnd1, and it is at the end of the series in icnd1, so I realize that there may also have been a lot of information going through your head by that point. So we'll do a brief review of what leased lines and point-to-point connections are all about, both at the layer 1 and layer 2. Then we'll get into the configuration. The beauty of leased lines is that they are very easy to configure. Actually, if you've got two Cisco routers on both sides, there's virtually nothing to it. But we're going to go a little beyond that. Talk about configuring them for PPP, which is the point-to-point protocol, and then we'll add on top of that PPP authentication. I'd first like to review some of the physical links that are in our WAN technology. What I have here is almost like a mini flowchart of how WAN connections look and how they physically connect in your environment. Up at the top here is, I guess, the starting point, which is a Cisco, this is a 2600 series router. Now on the back of that, you can see that yellow link right there. That is our Ethernet port, and that connects to the LAN. Right here is the WAN port, or I guess you could say a WIC slot. That stands for WAN interface card. Now you actually can put one of 3 different cards inside of that slot, and there's even more than what I'm showing here, but these are the most common. Right here are the traditional serial port connections. The one on the left is known as a WIC 1T, which is the old serial style connector. It's still all over the place though. It's got plenty of those. The one right here, this is known as a WIC 2T. They re-engineered their serial interface connection on Cisco routers to where they can get 2 WAN interfaces per slot. Pretty powerful. Now let's first talk about these 2 interfaces. If you purchase one of these cards and you've purchased a lease line, let me just get a brief drawing over here. Let's say that you have a router and that is supposed to connect to another router in Texas. And we'll say this router is in Arizona, where I am. Now that router connects to the LAN over here. Now this router, we would plug in right here. This is the physical view of my logical diagram down here. We would plug in one of these WAN ports. And that WAN port would then require a specialized cable. This is known as a DB60 connector, which would connect to that WAN interface over there on the left. Now that will then have that cable that runs to a, well, it looks very odd. You see the interface connection type right over there. That's actually known as a V.35 connector. That will connect from your Cisco router, that's the Cisco end of the connection, to this device, which is known as a CSU DSU. These have been around for decades, and those are the devices that manage the WAN connections. They set the pace, the clock rate, they do error checking on the WAN line. They're pretty expensive, but they really just convert from the V.35, or there's actually 5 different types of CSU DSU physical connections. This is just one of them. It converts from that kind of connector to it looks like just a standard Ethernet jack that the service provider installs. So if you're looking for a little simpler flow, you have the wall of your building right here. Outside is the grass and the trees that are growing, outside. The service provider comes in, trenches under the land, and marks this wall as the demarcation point. That's where their responsibility passes. They install a wall jack and they say, if anything on the right side of that wall jack breaks, we'll pay for it. And if anything on the left breaks, you'll pay for it. You run that cable, you can see from the wall jack, little yellow cable, to the CSU DSU. CSU DSU gets one of these specialized serial interfaces or serial cables. You buy those from Cisco for $100 or eBay for $10. And that will allow you to connect from the CSU DSU to the serial interface, and you buy the correct cable depending on what kind of WIC card you have, and that is what brings up your serial link. Now you see up here another physical option, which is to take a built-in CSU DSU. Technology has advanced. Like I said, these have been around for decades. They've figured out how to put all the functions of a CSU DSU on this little card. So if we were to be able to zoom into that blue writing, it actually says T1 CSU DSU right on there. That means it has a built-in one. That allows you to run the cable from the wall jack straight into this interface on your router. Pretty fancy. So those are the physical connections of what serial lease lines look like. In addition to defining a new physical layer connectivity, the WAN connections and WAN links define a new data link connectivity as well. It blows people's mind when they first find out in the WAN world, the wide area network world, there are no MAC addresses. What? Well, but how does that work? You know, is it a traditional response? Because we're so used to working with Ethernet, where in Ethernet we have MAC addresses, but MAC addresses are only Ethernet technology. In the WAN world, we have all kinds of different layer 2 addresses depending on the WAN link you're using. For instance, if you have frame relay, which we'll talk about a little bit later, DELCs are the layer 2. DELC is essentially, it fills the role of a MAC address. In ATM, you have something known as actually it's a VPI VCI pair, and that replaces the MAC address. In every kind of WAN technology, there's some other kind of layer 2 addresses and layer 2 system that it uses to communicate with the other side. Now, ATM, we're not going to talk about at the CCNA level. That's actually a more specialized thing. It's part of the CCNP tracks. Frame relay, we will. But in here, we're going to talk about the two least line data link protocols, and that is PPP and HDLC. PPP and HDLC are the two languages that you can speak when you speak to another router over a WAN link. Now remember, we're just doing a technology shift here. So far, and everything that we've talked about in this series and the previous series, all of the language that we spoke was Ethernet. And that's what allows me to plug a PC into a switch, and it can talk to a server or some other device plugged into the same switch. That's all using the language of Ethernet, a LAN language. Now that we've moved into the WAN, as we look at our lease lines, we have two different types of WAN languages that we can use between routers that are connected on a WAN link. HDLC is the default on all Cisco routers, meaning when you put that serial card into the router and turn it on, by default it's going to be talking HDLC. The beauty of HDLC is that it has extremely low overhead, which means it's pretty fast. It's not going to congest the link with all kinds of stuff it's adding in the header. It just says, okay, I will work. And the beauty of HDLC is in its simplicity. If you have a Cisco router on one side and a Cisco router on the other side, and you plug in that WAN cable that connects to the service provider, and remember, this is logical. We have our wall, and in the middle of this is the service provider, and hundreds and thousands of miles between these two, and then another wall and a wall jack and all of that. When you plug your cables together, it just works. As long as the service provider has done their side and everything's working in the middle, there's no configuration necessary. You just put an IP address on each serial interface that is in the same subnet, and you're good to go. The disadvantage of HDLC is this and that. It is Cisco proprietary, which means it only works if you have two Cisco routers, and it has no features at all. Meaning, if you're looking for it to do some kind of spazazzy thing, which we'll look at PPP in just a moment, on your WAN link, it can't do it. That's why we have PPP. This is our second choice. If we want to convert over and run PPP, it's just one command, and we'll see that in the next slide. One command that you type in, and your routers are now running the point-to-point protocol. The beauty of PPP is that it's industry standard. So I could have a Cisco router here connected to, we'll just throw out Juniper, a company I have been very impressed with lately, a Juniper router on the other side, and they can both speak PPP and it will work just fine. You have moderate overhead, which means it's not high overhead. It's not really going to bog your WAN link down to use PPP. And as a matter of fact, if you don't turn on any of the features, then you're really nearly equivalent to HDLC. So it's not too much overhead, but PPP is feature-rific. Matter of fact, there are 4 major features it supports. Number 1 is what we're going to set up in here, authentication. That means that you can add a username and password to your WAN link, and the other side must provide that. Now, on lease lines, you can do it, and we're going to set it up in here. It's not very common, though, because the only way somebody is getting on this lease line is if they walk in the building over here, kick over the administrator and, tie him up in a chair on the side and pull the Juniper router off the WAN link and put their own router on. In that case, you're not so much concerned with them getting into your network as you are the administrator tied up in the office over there. So it's not very common that people put authentication on WAN links, but PPP can run over just about any type of WAN connection, like modems. When somebody dials into your network, if it's just connected to a phone line, you want to make sure that you prompt them for a username and password, because if not, they're just going to dial a phone number and they're in. So that's where authentication comes in very handy. Second, compression. You can make a trade-off on your router where you trade some processor cycles, meaning you're going to cause your processor to get used a little bit more on your router, for bandwidth. Because what will happen when you turn on compression is as data is sent from your LAN through the router and on the WAN, it's smushing it down. If you think of a zip file, that's the same concept. It's smushing down data as it goes over to the WAN, and when it reaches the other side, it unsmushes it. So you have the full file there again. Now, the great idea about compression is that you actually use less WAN bandwidth to send the same amount of data. You're just smushing it down before you send it. The problem with compression is it can eat up quite a few processor cycles. So if your router's already bogged down and you turn that on, you've doomed it. It's going to crash, or it's going to be overwhelmed, because compression can eat up quite a bit depending on how busy that WAN link is. Third one is called callback. This is primarily used on modems, and when you dial into the modem and authenticate, meaning type in your username and password, the router immediately hangs up on you and dials you back at a predefined number. That's pretty secure in the sense that that ensures that somebody can't just steal your username and password and dial in from some other location. If you have maybe a home that you dial in from, that is the only location or only phone number that's allowed to dial in, because the router will dial you right back. It's also good because you consolidate long distance. Like if I was dialing in and making a long distance call to dial up to a network, I could have it hang up and the company foots the bill, and they'll call from their corporate center where they probably get cheaper long distance rates than you do at home. Last but not least is the most famous feature PPP is known for: multi-link. Multi-link is a system that you can employ that allows you to combine the bandwidth of multiple WAN connections into one. In recent years, the price of dedicated T1 lines has gone down. But T1 doesn't give you too much bandwidth. It's just 1.544 megabits per second. So you could add a second T1 and a third T1. And what multi-link allows you to do is bundle all of them together and combine the bandwidth into one. So it would be 1.5 megabits per second times 3, so you're at about 4.5 megabits per second. Multi-link exactly load balances over all of these. And I don't know if that was the best way to say that, but it is precise load balancing, where to the bit, every single WAN link will get the same amount of data sent across it. And that's what truly combines the bandwidth into one. Now let's turn our attention to the configuration of PPP. We're running HDLC right now, and my focus is going to be on this WAN link between router 2 and router 3. I set that up just connecting the two using it's a serial crossover cable, which is used to simulate a leased line environment. But this is exactly how it would work if you were connecting using a service provider between these two offices. So let's hop on over to router 3. And let me just clear this off. I was doing a little verification beforehand. On router 3, I'm going to do a show IP interface brief. And we can see this is the router and the branch office over here with all the loopbacks that we were using for the previous videos. Right here is our serial 0/0 interface. Now I'm going to type in show run interface, we can focus it in on just interface serial 0/0. That filters the running config down to just that. Underneath interface serial 0, I see the IP address. We have a summary route that we were using when we set up EIGRP, and no fair queue, which is there by default. That's a quality of service mechanism. I don't see anything about PPP or HDLC. So to really see what it's configured as, I need to type in show interface serial 0/0. And underneath here, I can see serial 00 is up, line protocol is up, that's good. Right here, encapsulation HDLC. That's the default. As a matter of fact, if I go underneath that serial 0 interface and type in encapsulation HDLC, that's the default command, so I will not see that in the show run. I don't know if you've gotten used to that yet, but when you're looking at the running config, it actually will filter out commands that are typically there by default. Just like you look under serial 0/0, we had to type at some point no shutdown to bring that link up. But you don't see the no shutdown command. You only see if it's shut down because it's assumed not to be shut down by default. So we've got router 3 running, and router 2 is the identical configuration. Let me jump over to there. Oh. There we go, router 2. I'm going to do a show IP interface brief just to make sure I see my interface. It is serial 0/1/0. I'll do the same command here, show run serial 0/1/0. Oh, forgot the interface. Show run interface. There we go. Looks very similar. This side's a DCE circuit, so it's setting the clock rate in a lab environment. And I do a show interface serial 0/10 and verify once again that is also running HDLC. So the initial PPP configuration I'm going to do is very simple. Turning it on. I'm going to go on router 2 under interface serial 0/10. That's our link over to router 3. And type in the command encapsulation, and you can see I have plenty of options, but really the only two that work on point-to-point circuits is HDLC and PPP. As soon as I type that, I've changed the data link language for that serial interface. Now look what happens if I do a show IP interface brief. I see my serial 01, it shows it's up, and remember this first column, the status, represents physical. It's physically up, there's clocking on the line, I've got a cable connected, we're communicating physically, but this represents the data link layer. Data link layer is currently down because R2 is PPP, R3 is HDLC. So I'll jump over there, I got my numbers off here, jump over to router 3 and fix it. Do the show IP interface brief here. I notice that serial 0/0 is in the same state. Encapsulation, PPP. Give it a few moments, and we should see that interface come back online. There we go. You see the line protocol right here has changed to up, and we got our EIGRP neighbor back. Go back and do our show IP interface brief, and you see we're communicating. Show interface serial 0/0 is now running PPP. You can see that we are now communicating using the industry standard language, and that's all there is to it. If you were connecting to a non-Cisco router over a WAN link and all you wanted to do was run base PPP, that's the only command you would have to type. Now you can see LCP is open. That's the link control protocol. That's what negotiates the PPP features. If there was some kind of problem with, for instance, authentication, compression, multi-link, where they couldn't negotiate and figure out common ground, or a wrong password is typed in, it would say LCP closed, because LCP handles all those features. You can see also right here, open, IPCP, CDPCP. PPP uses things known as control protocols. So when you see IPCP, you're seeing the IP control protocol. That is what allows the TCP IP, the IP protocol, to work over a PPP link. CDPCP is the Cisco Discovery Protocol, control protocol. That's what allows CDP. You remember this? Shows CDP neighbors. That allows it to work over a WAN link so I can still see my neighbor even though they're using a PPP connection. Cool. So that's the base configuration of PPP. Now let's add authentication. There are two types of PPP authentication that have been developed over the years. The old one is known as PAP, the Password Authentication Protocol. The new one is known as CHAP, the Challenge Handshake Authentication Protocol. PAP is very rarely used. As a matter of fact, I can, with near perfect confidence, say you will never see PAP used anymore. And the reason why is all of the username and password, when it's sent, is sent in clear text. So if someone had some kind of packet sniffer between these two routers, they would be able to see the username and password come right across, open up the packet, and go, oh, that's what they're using. So PAP is just not used anymore. Nowadays, people use CHAP, the Challenge Handshake Authentication Protocol. Now, without getting too deep into it, what CHAP does is never actually send the password over the wire. It's a little weird. It'll send the username, but not the password. It will send a password hash. So here's the idea. The way CHAP works is not through encryption, but through hashing. There's a big difference between those two, and it took me a long time myself to come to an understanding of what that meant. Because encryption and hashing accomplish the same goal, but in very different ways. Encryption, if you were to say encryption, you would be talking about something that takes the data, let's say this is the data, ENC, and runs it through a mathematical formula so it's all scrambled when it comes out. It's just, it looks like a swear word. It's just a scrambled mess of that original thing that was sent. So if somebody captures that, unless they have the decryption formula, they can't figure it out. So a decryption formula would come in and say, okay, well, let's put this back into that mathematical formula and spit out ENC that was originally what is sent. Hashing. Hashing is very different because it uses an irreversible formula to scramble the data. Here's what I mean. Let's say hash is the data that's sent. It will put that word hash, that's the data, through some super complex mathematical formula and will end up with an answer. 596AB9621. The answer is what is sent across the wire. Now, in router 2, if these two are authenticating, when router 2 gets that answer, when they get the hash, they will not be able to decrypt that because remember, this isn't encryption, it's hashing. The only way it can know if this is valid or not is if it has the same thing typed in on this side and it can run it through that irreversible formula and the answer will come out to be the same. So, this brings up a big point. CHAP does not use encryption, it uses hashing. In order for it to work correctly, we must type in the same password on both sides because all it will send across is the hash of the password. Like I said, the password is never actually sent. And when I didn't understand what hashing was all about, I didn't understand that statement. Well, how do they know if they got the right password if you never actually send the password? But they don't. They just send the hash of the password, the result of some mathematical formula with this hash plugged in there, that data, and it gets to the other side. It looks at the answer and says, well, I can't reverse engineer that. I can't quote unquote decrypt a hash. So let's say this. Let me give you an example. If I wanted to have authentication going between router 2 and router 3, I would have to type in the same password on both sides. We'll say the password is Cisco. Password is Cisco. Once I have that typed in both sides, this one, if it needs to authenticate to the other side, will run this through a hash. It's technically known as an MD5 hash. So it will hash that up, come up with some gibbly-gook answer, take that answer, this is my gibbly-gook, send it across the wire, router 2 gets the answer, has the same password typed in, runs that through the same irreversible formula, the MD5 hash, and comes out with its answer, compares its gibbly-gook to that gibbly-gook, and says, oh, they're the same. We must be using the same password, thus we are authenticated. Side note, this is why when you go onto a router, oh, let me move my window back in here, and you do let me do a show run. No. Let me do this. I'll do enable password Cisco 1. Service password encryption. Now I'm going to do a show run. When you're looking right here, think back to icnd1. You remember the difference between enable password and enable secret? The enable password was the one that's stored in clear text. At least it was until I type in service password encryption. This is an encrypted version of the enable password, an encrypted version of Cisco 1. Now, hold on one second. I'm going to go to google.com, shoop, Google, and type in break Cisco. Oh, you can see I've done this before. Break Cisco password. Google search. Right here. The Cisco password cracker. It's the first hit. Go ahead and click on that bad boy. Look at that. Type 7 password. I look over here. My enable password is a type 7 password. If I take this, copy it to my clipboard, and paste it into this website, paste it into the website. Are you following me here? Okay, crack. Oh, what's the moral of the story? I love it. Don't use it. Don't use that because this is encryption. Encryption can be broken because you can always reverse the formula. You can do a decryption formula, which is exactly what that website does. Notice enable secret 5. A lot of people think, oh, well, 5 isn't as good as 7 because it's a smaller number. 5 represents MD5 hashing. When you're using your enable secret, this is a hash of whatever your enable secret is. You cannot reverse engineer that. So if somebody gets that hash, the only way that they can break through it is through a brute force attack. And what that means is they will use a program that will start trying passwords. It'll start with maybe the number 1, 2, 3, 4, 5, and it generates what hash the number 1 would generate. Compares it and says, is that the same? Nope, must not be that one. Good program, not good, but a program that you can use to do that is known as Cain Enable. If you go to Google and search for Cain Enable, that's a program that will do a brute force attack of an MD5 hash, but it can't reverse engineer this. All it can do is keep trying different combinations to see if it can come up with the same hash as that. If you make your password long enough, you'll never be able to do that. So that's the big difference. And I know I've talked a little longer on that, but I want you to know how good CHAP really is. CHAP is using that MD5 hash, which makes it virtually, and I knock on wood when I say this, unbreakable until some other 12-year-old Swedish girl comes along to break through this. But that's the idea of CHAP. Now, that's the concept. Let's configure it. There are really 2 steps to configure PPP authentication. Create a user account and then turn it on. I'm going to reverse those steps because I want you to see what happens when authentication isn't working correctly. I'm on router 3, which is our far end router. I'm going to go under that serial 0/0 interface and type in the command to turn on authentication. It is PPP authentication, and then what kind of authentication you would like to use. Now, our routers between each other use CHAP or PAP. And I mentioned PAP is no longer used by anyone, so we can use CHAP. Now you notice a few others in here like EAP. I'm not even going to touch that one. That moves into some newer technology out there. Some people call it 802.1x. It's a newer type of authentication. It's pretty fancy. Down here we have MS CHAP and MS CHAP version 2. Microsoft came out with their own versions of CHAP. So if you're dialing up to a router using a Microsoft Windows client, you'll have to use MS CHAP or MS CHAP version 2, which is a little more secure. But we're authenticating our routers, so I'll just type in PPP authentication CHAP. That is what I would like to use. Now, as soon as I do that, you notice that my line protocol on my serial interface just went down. The link died. If I go back and do a show interface serial 0/0, you notice it says encapsulation is still PPP, but LCP term sent. That means the termination signal was sent. I, router 3, sent a termination signal to the other side because I was told by the administrator to require CHAP authentication. The other side wasn't prepared to handle that, so you are terminated. You are not successfully authenticating to this router. What we need to do, and before we should have done that, is create user accounts. By default, when I have routers that are going to use CHAP authentication to speak to each other, router 2 will come across and say, hello, I am router 2 as my username. My password is, it's the gobbledygook, the hash that's generated by CHAP. Now, router 3 is going to look at its user database and say, okay, do I have a user account defined for router 2? And if so, what's router 2's password that's tacked onto that user account? Let's say I'll put Cisco as the password. It will hash up that password and say, okay, well, based on the user account I have for router 2 on my router, I came up with this gobbledygook. Does it match the gobbledygook that router 2 sent me? Do these hashes match? If so, that is a successful authentication. So let me show you how to create the user account. I'm going to go on router 3. I'm going to type in username R2, password Cisco. Notice I'm in global config mode. I typed in username. This is the host name of the router that's coming in, R2, and its password that it should be sending is Cisco. But remember, it won't be sending you that password. It'll be a hashed version of that. So router 3, you must hash that in order to get the other side. Now, when we're doing PPP authentication on a lease line, it actually does something known as two-way hash, meaning the routers will authenticate each other. Router 3 will have to supply a username and hash to router 2, and router 2 will have to supply a username and hash to router 3. They both check to make sure they have the right passwords. If so, then they are good to go. Now, the way that two-way hash works on a Cisco router is both sides must be configured with the same password. So when I go over to router 3, or sorry, router 2, router 3 is done. I'm going to hop over to router 2. Go into global config mode. I'm going to do the exact mirrored configuration. Username, R3. Password, Cisco. This password must match. Oh, look at that. You see it come up? It must match the password that router 3 has for router 2. If these are different, the authentication will fail. So last thing I'm going to do on router 2 is go under that serial interface and type in PPP authentication CHAP. We now have successful authentication going between each other. Let me show you how you can see this happen. I'm going to type in debug PPP authentication. That will let me watch these two routers authenticate each other. Now, it's already done. Meaning the line is up, they've authenticated. So what I'm going to do is I'm going to cause a catastrophic network failure and shut down serial 0/1/0. That will force the interface to go down, go into administratively down state. And when I do a no shutdown, the PPP will have to authenticate between these two again, and we can watch it happen. So I'll do a no shut, exit back out here. There we go. See what happened here? It says PPP using default call direction. This is a dedicated line. Oh, I've noticed authorization is required. So I will send a challenge. It says there is a challenge from router 2. This is being sent from router 2 to router 3. At the same time, it received the challenge from router 3. So they're challenging each other. Do you see the two-way hash happening here, or the two-way authentication? They both challenge each other. They said using the host name from an unknown source, using the password from AAA, that's the local user database. So we have challenge. We respond to the challenge. Router 2 responds to router 3, and router 3 responds to router 2, receives the login, the host name, and the password hash. Sends the author request, and we won't get into what that is. But down here, you can see success. We have success. The challenge is working between these two, and they have successfully authenticated. If one of those passwords is mismatched, you'll see a fail here, and the link will never come online. That is the theory and practical configuration of PPP authentication. So let's wrap up. We saw, first off, a review of the point-to-point protocols, looking at the physical layers with serial interfaces and the data link layer of HDLC and PPP. We then got into the configuration of WAN links, looking at the initial HDLC, converting to PPP, and then adding PPP authentication on top of it using CHAP. I hope this has been informative for you, and I'd like to thank you for viewing.